So the very beginning thing that I want to talk about first is that like the whole purpose of why I put this together. Basically, it's twofold. One is I like to be able to think that I help people gain the tools to not be afraid of their data. I want to improve your relationship with your data. And so just not to be afraid of it and be able to just like to go in and know how to think about your data in terms of analysis. The second thing, which I think people really appreciate, is the fact that a lot of people know how to program in R, they know the basics, they know like some tips and tricks, but they don't really know what they can do with that. And R is a really powerful tool. I've been using it for all my analyses, from like images to videos to 3D models, and basically showing people what you can do with it, getting people thinking outside of the box of what you can just do in R, what you would learn in a typical class. Like that to me is really important, because having an idea of what you can do is really empowering in terms of like you going out there and finding out how to do those things. And so I thought it'd be really nice to start off with this example, because to be honest, people have asked me about these two things multiple times, and I never knew how to do it. And I just learned in the past couple months, first of all, how to do a split axis plot. So if you notice, this is the same plot, same y-axis, this is the same x-axis, but there's a break right here. And a lot of people have been asking me how to do that. And the other thing that people have been asking me is, it's very easy, as you'll see, to fit normal lines to data, like a single straight line. But in order to fit a curve, a second order polynomial, third order, fourth order, which you typically see in papers, like we fit this fourth order polynomial to our data. How to do that in an intuitive and easy way. So I'm going to combine both of those things together. Hopefully, first of all, starting by how do you fit different types of curves to the data. All right. So just to orient you on RStudio, if you've never seen RStudio before, I've moved my panels around just so it's easier for people to see. But up here is your console, right? So your console, this is your basic where you would normally do your R. So if you just type in 1 + 1, you get you can do all these things. If you want to get a list of numbers from 1 to 10, you can do that. This behaves exactly like your R terminal does. And I like to think of this space as your place, like your playground. This is where you test out your ideas. Whereas over here on this side, this is your text editor, and this is where you basically make your code. Where you save your variables, you call your variables and whatnot. And if you want to inspect something, then you'd mess around with it over on your terminal side. But this should act as a file that you can run over and over and over again and get the expected results every single time. What gets really complicated is that when your scripts get longer and longer, you're gonna have variables that should be there that aren't there, and that get really messed up, and you get really confused. And so I really believe in being able to make a script and practicing making scripts that you can run every single time and get the results that you expect every single time. And so let's just start off with the data, right? So hopefully if you had downloaded it, it's right here. It's a simulated data1.csv. Very quickly, what a CSV file looks like. So I'm just going to open it with a normal text editor. You can open it with Excel, but just to see what it looks like. It's what you would expect in terms of there's an X column and a Y column, and it's kind of hard to see, but the columns are divided up by comma. The CSV file format is, in my opinion, the best way to deal with data. It's completely unambiguous, and you'll make your life a lot easier if when you have the chance to save your data, you save it as a CSV. Yeah. So the first thing you want to do is set your working directory. The command for it is setwd for set working directory. And again, I like using RStudio because, so what you would need to put in here is a path, right? The path to the folder where your data is, your downloads folder, your source folder, whatever. The reason I like using RStudio is because once you have these quotation marks in here, once you hit tab, it will look around. So for example, for Unix-based systems, I guess everyone here is using a Mac, To get to the root, it's a ~/ and once you hit tab, it'll basically look through everything. If you have your file under your downloads, it's right there. I have mine under Dropbox. I have mine under something called argets, and as you can see, it's very easy to navigate using this. So once you have it where you want, in order to run it, you could copy and paste it into the terminal, but there's a shortcut which is Command-Enter. Command-Enter will basically copy and paste the line where your cursor is and put it into your console, and it just ran that command. In order to see what's in there, to check where you are, you could say get WD, right? So that hopefully will return that we're in where we think we are. And I also like doing list.files, just so you can see what's in there. So list.files looks inside your working directory, and it lists every folder, every file that exists. The one that we're looking for right here is simulated data 01.csv, so that tells me that we're in the right place. Also, don't get confused with list.files and ls. If you do ls, open close parentheses, ls basically gives you every variable that you've created in R. We haven't created any variables yet, so it's returning nothing, right? But some people get ls and list files mixed up. List files, I'll even write a comment right here, looks in the working directory. ls looks at variables in R. Cool. And also, this is up here on the screen, but I also provided this link here, which is a window into my PC, or I guess my Mac. So you can see that there is a file here, 101716 fitting curves. So every time I hit save, this should update, and you can see it. It has all the context coloring as normal R, so you can always look back there. The first thing I want to do is import data. What do? Right, so there's a function called read.csv, and also if you forget names of functions, you know that it's read something. You can hit tab and you see all of the functions that are in here that start with read. So the one that we want is read.csv. And if you're curious about what this function does and what goes into it, you can type in read.csv, and that will open up the help file. This is my go-to place. I often find that you're going to have to search forums sooner or later, but as much information as you can get from the built-in documentation, the better. So for example, read.csv, you can see here the things that go into it, right? It's looking for a file, you have to set whether the header is true or not, set all those things. We can go into that later. If you have a very simple CSV like we have that's formatted correctly, you can just go in, find it, and then when you hit run, you see there is your CSV, and it looks more like a table, right? So again, running this just prints it out to your terminal. What you want to do in order to analyze it is you want to save it as some variable. So I'll just call it my data, and then this symbol here, basically it's an arrow that assigns whatever this function outputs into this variable. So when you run it, nothing really happens, but now when you type in my data, you get that back. And also as a check, now when we type in ls, we can see that now there's something that we've created that says my data, so that looks good. Other things I like to do with my data is I like to inspect a couple things about it. The most common thing I do is head. So when you do that, it lists the first couple rows. You can quickly visualize, all right, I have an X column, I have a Y column, and these look like my X's and my Y's. Another common thing that you do to inspect your data is maybe straight off, like right off the bat, you want to plot it. It's super easy. It's a plot function. It'll take an X and it'll take in a Y, right? And so you want to feed it an X and a Y, and you want those X's and Y's to be here. So you want basically some way to access the X column. You want some way to access the Y column, and you can do that with the $sign. So if you type in my data $, you'll see that when you hit tab, now you can select this X column or the Y column. So when you hit X, it gives you all the numbers in X in the straight list, and you do the same thing with my data Y. Right. And so now for plot x and plot y, you want your x to equal my data, $x, y is equal to my data, $y, and when you run this, you get a nice simple plot. I'll save that really quick. Whenever you have like an Excel type of data structure known as a data frame in R, things are divided up into columns. Yeah. And actually the way to think about data frames are a list of columns, right? You have a column named X and a column named Y. So that $sign allows you to go into the data frame and say, I want the column that has this signifier, in this case the X, in the case the Y. Another way that you can do it, and this is also good to know, is you can sometimes do a square bracket. That's another way to subset something out. And if in quotation marks you put an X, that's another way to get the X values. They're not exactly the same, but sometimes this way of doing it is more helpful than others. So the other way that you can do it, so say that it didn't, and we know that we want the first column.
Yeah, all rows in the first column.
So what you can do is you can do this subsetting trick again. And now what it's expecting in terms of a subset is it wants a row number and it wants a column number, right? So in this case, on the left side of the column, this is your row number. On this side, this is your column number. If we want all rows, we leave it blank. If we want the first column, we do 1. You see that gives us the first column.
Nice.
All right, so the first thing we're going to do is we're going to fit a line. You need to call a function called ln, which stands for linear model, right? And inside this function, you basically are going to put a y tilde x. Now, what this tilde means right here, you can think of, if you want to translate it into English, this means explained by. So in this case, our linear model is y explained by x, right? And so now I just put placeholders in here, but now we can replace this y and we can replace this x with our actual y and x. So what would our y be? So we go with my data, we go $, and then we can pull y. And then for x, we want to do the same thing, $x. And when we run that, no errors, and we actually get estimates for this. So when we're fitting a line, y equals mx plus b, we need a slope and we need an intercept. Here's our intercept, and here's our estimate for slope. Right? And what you don't have to do this step, but I think it helps with the organization a little bit, is you could save this to a variable. So if we call this line fit, now when we type in line fit, we get those numbers back. And the reason why this is cool too is now there are things hidden within this fit that you can recover. So now if you do a $sign, you can now see that, oh, there are things in here like the fitted values and QR. It has something to do with the decomposition of the matrix. But coefficients is usually what we're after, right? So now if we do coefficients, we see that, oh, there's the intercept and there's the slope. And so this is just a list of numbers. This is the first thing in it. This is the second thing in it. So if we want the slope, we can do square bracket 2, and hopefully that'll just give us this number, right? So that's a really easy way to like functionize this and like have a way to get the slope of your fits every single time. And so the next thing that you might be asking yourself is like, well, when you fit a line to something, you want to know whether or not the coefficients that are fit to it are significant or not, right? And because we've fit this linear model and we have a variable right in there, it's super easy. We just have to do a summary of line fit. Running that will punch out a summary table. Let me make that a little wider so we can see everything better. Right, so again, here's your intercept and here's your slope. These are the estimates for those values, right? So that should match up. I guess I cleared it, but this should match up with the estimates from before. But now we also have standard errors, and here are the p-values. So we can see that the estimate for intercept is 0.02, but that's not highly significant at all, whereas the slope has a significant estimate of 0.88. Right? So if we've gotten to this step, it's very easy to take this and plop a line down based on these values without having to do anything extra. because there's a function called Beeline. This is a useful function for adding lines of a line to any plot. So for example, if you had the slope and the intercept, you can use your A and your B here. So A is the intercept and B is the slope, and the reason I know that is because it says here the intercept and slope for A and B. If you just want to add a horizontal line, you could do H. So if you just wanted to do add a horizontal line at 0 just to see what it looks like, you can do that. You can also add in a vertical line, let's say at this cutoff here at 0.2. Too many equal signs. So this is just a very easy way to put lines onto your plot. And the thing that it does too is if you just put in your line fit, just like that, it will take your linear model and it'll take those the parameters that you estimated and drop it on. And so what I'm going to do is I'm also going to add a couple things to make this stand out, because now it's a little bit hard to see. So let's change it a different color. Let's make the color purple, and let's make the line thicker. That's LWD for line width. By default, that's 1, but let's just make it 5 and blow it up. And you can see now there's a nice thick purple line right in the middle. The one thing I'll mention about doing lines this way and why I don't typically like using AB line for figures on papers is that this line gets drawn all the way across. That could be fine if you're willing to make the assumption or the implication that you can extrapolate the data, but typically when you fit lines to data, you want to only fit lines to the observed x values that you have. And so there's no way that you can basically truncate this line using AB line. What you can do, however, is use another function called predict. Now what predict does, specifically we do predict LM, what predict does is you could throw in any linear model in there, and it will basically look at the x's that you have in your data, and it'll put the y's of those x's on the line, if that makes any sense. So for example, it'll take this x value, and instead of reporting a y value up here, it'll now report it on that line down there. And I'll do the same for all of them. So for predict LM, you can just put line fit, right? Let's see what that does. So like right now, it just punches out a whole bunch of y values. And again, these y values correspond to every original x value, but now it's been adjusted so that they fit on that purple line. And so what you can do is you can save this to something, call it predicted y. Now you have this list of numbers called predicted y, everything's good. I'm going to reset the plot just to get all this stuff out. The only way you can actually do that is to replot it. So I'm going to say my x is my data $x. I'm going to do y is equal to my data $y. Reset all of that. So you'll notice that every time you run the plot function, it basically resets everything. So you can't use the plot function to add things on top of an already existing plot. So for example, this AB line, it's a lower level function that doesn't clear out everything. So two other functions that you can use that add things to it are points and lines. Right, so for points, it takes the same thing. X is equal to whatever you want. Y is equal to whatever you want. In this case, what should our X be? Yeah, so I'll do that, and our Y. Yeah, so I'll do that. We'll change the color so we can see it better. Again, I'll just change it to purple. And now when we plot this, there are points in purple, right? So these should be 1-to-1 again for every point. For every black point, there should be a purple point, but the Y position has been changed and shifted so it fits on that line. And we can do the same thing. I'm actually just going to copy and paste this. Put this in lines. Right, so we run that, we get that line. And now you'll notice because it's a 1-to-1, it doesn't extend past our original data. So this is something I would be more comfortable putting into a paper. So now we're gonna go into some new stuff. It's gonna be fun. So the first thing I'm gonna do is I'm gonna reset the plot and get that out of here. Just do that. It's actually very similar. Doing a second order polynomial or a quadratic is actually very similar to doing a line. We're still going to use the ln function, right? We're still going to have that basic formula of we have y tilde x. The only difference is we're going to have to do something weird with x, and we're going to have to add another parameter here, which is we have to specifically say which data set we're working with. So let's just do a line really quickly. This would work, right? So if we look at my data again, we notice that there's a column that says x and a column that says y. You'll notice here in this linear model, we don't do any dollar signs, right? Like we did, where is it? Somewhere up here, where we had these dollar signs. But instead, we have to specify what data set or what data frame these x's and y's are coming from. Well, you'll notice that this will run perfectly. This is the trick that I learned. You have to do it this way if you want to fit polynomials in the way that we're going to do it. If you don't do it this way, so for example, if you had my data dollar sign and my data dollar sign, it'll fit, but it won't give you the results that you think it should. And so this is a super important step. Actually, I made a note down here because I tried this last night and I could not figure out how to do it. So I'll just move that up here. And so how do you do a second order polynomial? I'm going to copy it and paste it. It's just a little faster. So the only thing that we need to change here, now that these y's and x's are being referred to properly, is this x. Instead of it being a singular x, you might think you want something that's like x plus x squared, right? Like the normal formula for a quadratic is a plus bx plus cx squared. The way to do this in R, instead of doing it that way, is to call a function called poly. Here we can say x, it should be just x, right? So in this case, poly is looking for an x, and that x, we're telling it to be x in reference to my data, right? So that's a little confusing because it just says x equals x, but just keep in mind that, you know, the polynomial function is looking for an x, and that x is the x column in my data. That's an important distinguishing thing to make. And the last thing we need to do is, for degree, we just put in 2 for a second order polynomial. And now when we run this, we'll see that now we have more estimates. We still have our intercept here, but now we have this, which just says this is our first x, our linear x, and this is our second x, the x squared. And again, we can fit that, or we can save that in a variable. I'm just going to call it order 2 fit. All right. Cool. All right. So let's see what this looks like in terms of lines, in terms of points. So we're going to start off with the points function. What should my x equal here? Let's try that. And what would my y be? So we're going to do the predict function, and object, I'm just going to put in my order 2.fit. And I'm going to call this y predicted. All right, so now y is going to be y predicted, right? And we'll just give it that purple color again. And we'll see what that looks like. Looks like a quadratic function. Cool. But what you'll soon see is we're not quite finished, because when we try to do lines, get that. And again, that's purely because our x values aren't ordered in here, right? So there's a bunch of x values over here, and the next one is way out there. So in order to fix that, we have to order our x values. And there are different ways to do it, but I think this is the most informative way, is to get an ordered set of x values, and you can do that using the sort function. So in sort, you just put something in there. What we want is my data $x. So now if we look at my data $x, we can see that these aren't sorted, right? So there's an 8, 7 down here, and there's a 6, 7 down there. But now when we look at ordered x, that looks about right. So it goes from 0, 0, 1 to 9, 9, 4. Our fit is still applicable, right? We haven't changed anything about the coefficients, so we don't have to rerun that. But what we do have to do is fix our y.predicted. So we still use the predict.lm function or predict function. They're basically the same thing. We want to put in our fit, which is our order2.fit, right? And so here's the tricky part that I learned. There's a thing in here called new data. So if we just look at predict.lm really quickly, look at the manual, we'll see that there's something in here called new data, an optional data frame in which to look for variables which to predict. If omitted, the fitted values are used, right? So that's what we did before. We used every x value that was already there. But because we sort of changed the order, we have to provide the new set of x values to it. And the tricky part here, which I've skipped so many times and I don't know why, is the fact that it has to be a data frame, right? So if you just put ordered x in here, if you just said new data, ordered x, and you run this, you're going to get an error. And I never understood this error, and I never bothered with it. What you want to do is set this as a data frame. And basically, to set it as a data frame, you're taking a list of numbers and you're making it into, very specifically, a column named x, right? So to do that, you do data frame x equals order.x. So again, what this is doing is it's taking your flat list of numbers, your unidimensional set of numbers, and it's putting it into a column, a data frame, with the column label x, and that should match what's in your original data set, right? So if your thing was called time, this would have to be time. So now this will run, I think, without an error. So we got no error, and now I'm going to reset the plot. Do that. Bless you. Do that. So now reset the plot. Put the points. So what did I do wrong here? Yep. So how do we change that? Yep. So we change that to ordered x. We'll do it again. So that looks better, right? And we've got to change it down here to ordered x. Now we run it. That looks a lot better. But there's still something wrong with this. Can anyone see it? Yeah. So because there are no x values in between this data point and that data point, it's just drawing a line between them. So that's not exactly what we want either. What we want to do is we want to predict a whole bunch of y values for, I don't know, like 1,000, 5,000 x values between here and there to get a really smooth curve, right? So I'm going to show you very quickly how to make your own x values. This is I use this a lot, which is the sequence function. And for sequence, there are things that, so I like to go from, and then you can go to to, and then you could either do by, if you know what interval you want to go at, but another way that I like to do it is length.out, where this is how many total values you want. So like I said, maybe like 5,000 is what we want, right? So we want to go from, it looks like 0 to 1, and we punch that out, we get 5,000 values from 0 to 1. Right? So what you can do is you can set this to new.x. Right? And so from there, you should be able to finish the rest of this problem. So we're going to have to repredict. We need to overwrite y predicted. So if we do predict lm, I don't think we need to change the fit at all because those what is it called? Order 2 fit? What do they call it? We don't need to change that because all that should be the same. The only thing we do need to change is this new data, right? And again, instead of saying new.x, we want to put this inside a data frame where x is equal to new x. That should do it. Let's see. I mean, if you feel more comfortable redoing the fit, you can, but it's not going to change. It's all the same, A, B, and C, right? So I think the trick here is understanding that once you introduce a new, like in this case, a high resolution X that's already ordered, you need to then run that, somehow link that to your model and recover the Y's. And you can see that looks more like a curve down there. And so I put as a practice down here to fit a fourth order polynomial to the data. And you can try that. The basic reason I put that down there is because I think it's important to realize what steps you have to redo, or if you don't want to think about it, redo all the steps. But basically, to fit a smooth data, to fit a smooth curve, we had to redo the predict step. If we do a fourth order polynomial, we have to fit a brand new polynomial to that. So it's just like an exercise in reminding yourself either where you should be picking up, or if you don't care, you just want to start over. So sometimes that's easier. It's really up to whatever you're comfortable doing, but I think it's important to realize that. Yeah, I mean, if you want it to be really correct, right? I think this is a good practice too. Instead of 0 to 1, instead of assuming that, you can do the min of my data $x, and then here's the max of my data $x. I was just assuming. So the next step, what we're going to do next week is now, you'll notice that there's that gap, right? And you'll notice that up here, we sort of eliminate that gap and have different resolutions on the x-axis. Very quickly, as a introduction to that, I just want to show that how to control the x-axis for one plot, right? So our x, right? So is my data $x, y is equal to my data $y, and when we run this, we get that plot that we're used to seeing. One very easy way to scale, for a lack of a better word, this x-axis is to add in an x-lim. So it's the limit of x. And what we want to do is we want to put in two numbers, the low number and the high number. To get two numbers, you have to use the C or concatenate function. And so let's say we're at, let's look over here, 0.05 is a good boundary. So we want to go from 0 to 0.05. Right. So if we run this now, we'll see that it's plotting all the data, which is useful because it's taking into account y values that don't necessarily exist on this view. Right. So this is auto scaling to the entire data set, which is pretty handy. And if we want to see the other one, well, we can just copy and paste it, and we can change that really quickly. 0.5 to 1. Right. And so you can, using these arrow keys, just bounce back and forth between the plots. You can see that the y-axis doesn't change; it's all scaled perfectly. The only thing that's changing is the x-axis. And so what we'll do is we'll combine we'll learn how to put two plots into one plot, and be able to scale it so that one is shorter than the other. But at least getting the dots up and getting the curve that's